me yet.
Is it lagging?
And now it's not, it's fine. Before it was lagging, so
Not now. Now is it good?
it's still lagging a little bit only, but it's still fine.
Okay. Yes, Maha and Sumaya. Can you hear me? Is it lagging?
No, ma'am. Clear.
Not lagging, Galvin.
But for me, it was lagging a bit for me.
Please check the network
Yeah,
connectivity at your end as well.
yes, ma'am.
Okay, let's start. So in our previous class, we were talking about how to prove that root 2 is an irrational number, how to prove that root 3 is an irrational number. We already know that it's an irrational number. We know that when we will find the log division method, when we will apply for finding the square root, we know that we will be getting a non-terminating, non-repeating decimal number. Okay, but here we have to prove it. Only we will write the statement that it is a non-terminating decimal number, it is not non-repeating decimal number, and hence it's an irrational. That will not work because this proof question will be for 3 marks, 4 marks will be there to prove that root 3 or root 2 is an irrational number. So obviously we have to follow a proper steps to prove it. Okay, now we were talking about first thing first, what is co-prime numbers. Co-prime numbers, co-prime numbers. Let me take examples. Suppose I am taking one of the number as a 9 and another number as 8. Can you tell me what are the factors of 9 and what are the factors of 8? Let's make the list of factors of 9 and the list of factors of 8. Please let me know.
1,
Perfect.
3,
Yes.
9,
9. Perfect. What are the factors of 8?
1, 2,
2, 4, and 8.
Perfect. Okay. These are the numbers which can divide. These are the number which can divide 9 completely, and for 8 also we have listed down the factors of 8. Now if I will tell you for what is the common factor, if we have to write the common factor from these two, what are the factors that are common in both the list? Anyone?
1,
Just one. Can you see? Just one. Common factor is just one. If this is the case, if we are listing down the factors of two number and only one is the common factor, okay, there is no other number apart from 1 which can divide 9 also and can divide 8 also. Okay, if we are having these two numbers, if we are having such a case where there is no other number apart from 1 which can divide both the number, then we will say this 9 and 8 are co-prime numbers. Now we will say 9 and 8 are co-prime numbers. Okay, apart from 1 there is no other number which can divide 9 also and 8 also. Okay, now if we will be taking another example, let's list down the factors of 6. Please tell me what are the factors of 6.
Ma'am, the factors of 6 is 1, 2, 3, and 6.
3 and 6. Perfect. And if we will list down the fact, factors of 4? Factors of 4.
Ma'am, 1, 2, and 4.
1, 2, and 4. What are the common factors? What are the common factors in this 2 list?
1 and 2.
1 and 2. 1 and 2, these two are common factors. Hence, 6 and 4, is it a pair of co-prime numbers? Is it co-prime numbers? Yes or no? Maha, Sumaya, and Galvin?
Yes, ma'am.
Yes.
Yes,
Is
ma'am.
it co-prime numbers? No, these two are not co-prime number. That's what I am saying, that if only one is the common factor, if only one is the common factor, hence it's co-prime number. If apart from one there is another number that is coming in the common factor, then it is not a co-prime numbers. 6 and 4 are not co-prime number. Like this you can understand it. Or one more way is there. You must think, is there any number which can divide 6 also and 4 also? Yes, 2 can divide. One is okay. One will be always, one will be valid. Apart from one, is there any number which can divide 6 also, 4 also? 2 can divide 6 also, 4 also. So 6 and 4 are not co-prime numbers. Okay. Anyone who joined just now? Aisha. Okay. So this is how we will be checking whether the given two numbers are co-prime number or not. Yes, Aisha, just now we have started the discussion of co-prime number. How we will be checking whether the given numbers are, whether the given pair is a co-prime number or not. What is the definition? The definition is, we have taken two numbers, 9. Here you can see 9 and 8. We have taken this two number and we are listing down the factors of 9 and factors of 8. Okay. Now Maha, Sumaya, and Galvin said that the factors of 9 are 1, 3, and 9. Okay. They said that the factors of 8 are 1, 2, 4, and 8. Okay. Now here we have to find the common factor which is common in both the list. Okay. Now common factor, we can see only one is the common factor. One is there in the list of 9 factors and one is there in the factor list of 8 also. So one is the common factor. If this is the case, only you are getting one as a common factor. One doesn't mean one number. It is not 2, 3, 4, not any other number, just one. One means one. Okay, the number 1. Okay, if you are getting only one as a common factor, then you can say the given pair are pair of co-prime number. Okay, how, what is the another way of understanding it? You need to search. We are having 9, we are having 8. You need to search, is there any number which can divide 9 also and 8 also? Is there any number which can divide both? Yes or no? Yes or no?
No.
No, there is no number which can divide 9 also and 8 also. Okay. One can divide 9, one can divide 9, one can divide 8. That is fine. One will always be there. But apart from one, is there any other number which can divide 9 also and 8 also? No. So 9 and 8 are co-prime numbers. Similarly, we have taken another example and we have taken a number 6 and a number 4. Now the same question. This is the process which I am showing to you, but we need to ask the same question. Is there any number which can divide 6 and 4 as well? Is there any number which can divide 6 and 4 as well? Yes, 2 can divide. 2 can divide 6 also and 4 also. So 6 and 4 are not a pair of co-prime numbers. Getting it? Getting what exactly is the meaning of co-prime numbers?
Yes, ma'am.
Now here also,
Yes.
Aisha, we have listed down the factors of 6, we have listed down the factors of 4, and when we have written the common factor, the factor which are common in both the lists, then we found that 1 is there and 2 is also there. 1 and 2, this 2. So I said that co-prime number definition only says that if there is a common factor apart from 1, 1 is there, that is fine. 1 is okay. But apart from 1, if any other number is there, then it's not co-prime numbers. Okay. So co-prime, here we have got 2 also. Apart from 1, we have got 2 also. That's why we are saying that 6 and 4 are not co-prime number. Are you going to list down every time the factors of both the number, and then you are going to check whether the given numbers are co-prime or not? No. This is not how you are going to check it. You just need to think that is there any number which can divide both the given number. For example, if I am taking a number 15 and if I am taking another number 8, now you tell me, is there any number which can divide 15 also and 8 also? Is there any number which can divide both 15 and 8 also?
No.
No. Yes. Galvin, Aisha.
No, ma'am. No.
No. There is no number which can divide both 15 as well as 8. Hence, we can say 15 and 8 are co-prime numbers. Getting it? Is it getting clear?
Yes, ma'am.
Now, co-prime number, when it will be in the fraction, it will be 15 by 8. We won't be able to cancel it. It is not possible to cancel it. Similarly, the first example we have taken and we just ended up with the conclusion that 9 and 8 are co-prime number. If that is in the fractional way, 9 by 8 or 8 by 9, we won't be able to reduce it to lowest term. Okay, because there is no common number which can divide 9 as well as 8. So it is not possible to reduce it. 9 by 8, it will be as it is. Okay, 15 by 8, we won't be able to reduce this fraction to its lowest term. Already it is in its lowest term. Okay, if we will be having our second example, however, 6 by 4. See, 6 by 4, if we are having these two, were not co-prime number. We have already realized that 2 is a common number which can divide 6 also and 4 also. So this pair is not a co-prime number. Now you can also see we will be able to reduce it. 2, 3 times 6, 2, 2 times 4, 3 by 2. Now 3 and 2 are co-prime numbers. Yes or no? Yes or no?
Yes, ma'am.
So this is how we need to be clear with the co-prime number, because now only again we will be proving that root 2 is an irrational number. Last day we have done it like very quickly. Today we have already discussed that we will be giving it proper time and we will learn it from the very basic. So this co-prime number we have already discussed. Now we were having one theorem. The theorem says that let P be a prime number if P divides A square, then P divides A. Where A is a positive integer. Where A is a positive integer. We don't have to prove this theorem. We have to understand this theorem, what exactly the theorem says. So the theorem says that if let P is a prime number, 2 prime number, 3 prime number, 5 is a prime number, any prime number we can take. If P divides A square, then P will also divide A. Okay, if P divides A square, then P will definitely divide A. If P divides A square, then P divides A. If suppose, for example, 2 divides 16, then we can say from here definitely 16 means 4 square. So 2 divides 4 square, then 2 will also divide 4. That is that when we will be taking an example, we can see in reality it is true. Okay, 2 divides 4 square, so 2 will divide 4. 2 divides 4 also. This we can see in the example. Similarly, if we will be taking 3 divides, let's say 81, then definitely 81 is 9 square. Then definitely we can say that 3 divides 9. We know that 3 divides 9 completely. We know that 2 divides 4 completely. So just with the help of example, we can see it's true. We just need to keep this theorem in our mind so that we can apply it directly in our question. So what the theorem says, if P is a prime number and if P can divide A square, then P will also divide A. Okay, definitely P will divide A. We have seen with the help of few example. If you want to take more example, please let me know. We will be taking that example over here. And you will find that if P is a prime number, if it is dividing A square, then it will also divide A. What is A? A is just a number. P is just a number. Okay. This theorem is clear to everyone. Aisha, Galvin, Maha, Sumaya. Is it clear, this theorem?
Yes.
Yes, ma'am.
Yes, ma'am.
Okay, let's move ahead. Now the next part, that is if we are doing the factorization of, let's say 6, we can write it as a 2 into 3. Okay, factorization of 6, we can write it as a 2 into 3. From here we can say 2 divides 6. 2 divides 6 completely, right? Right?
Yes, ma'am.
Similarly, if we are having, let's say any other number, that is 24. Okay, so we can do the factorization of 24. 2 into 2 into 3. Okay, one more 2 will be there, into 3. Okay, like this we can do the factorization, and here also we can say that 2 divides 24. Okay, so 24 we can break, even if we are not taking the prime number, if we are taking any other number, just 6 into 4. Okay, 4 into 6. This is how also we can write this 24. We can factorize 24, but that is not prime factorization. But here also we can make the conclusion. Here also we can make the conclusion. Even if we are breaking 24 is equals to 4 into 6, we can make the conclusion that 4 divides 24. 4 divides 24. That means 4 divides 24 completely. 6 divides 24 completely. Okay, we can make that conclusion because 24 is equals to 4 into 6. So obviously 4 will divide 24 completely and 6 will also divide 24 completely. When we are having the number, it is so basic. But when we will be having an expression like this, that m is equals to 2 into p. Now here it will create confusion. M is equals to 2 into p. Now if I will write that 2 divides m, is it making sense to you? Are you getting it? Yes, Aisha, Galvin, Maha, Sumaya, please let me know. If we are not having numbers, like right hand side, left hand side, everything is not just the number. If we are having a variable like this, m and p, then also we can write it like this. Yes or no?
Yes, ma'am.
Right? Everyone getting it? Similarly, if we are having k is equals to 2 into q or maybe 3 into q, we can say 3 divides k completely. Or if we are having q square is equals to 2 into k, then we can say 2 divides q square. Getting it? Yes or no?
Yes, ma'am.
Similarly, let's say we are having p square is equals to 3 into q. What can be written over here? Please tell me.
3 divides p square.
Exactly, 3 divides p square. Completely, 3 can divide p square completely. Even if we are not writing it after p square, 3 divides p square. After that, even if we are not writing completely word, then also we need to understand it is completely divisible. Okay, so this much is clear. Similarly, let me take the same cases. If we are having 6 is equals to, okay, 6 is equals to 2 into 3. We have made the conclusion that 2 divides 6 completely. Okay. Similarly, we have taken few more example, but if we will be having the reverse case, that is a statement is given. A statement is given. The statement says that 2 divides instead of 6, I am saying, let's say 2 divides p. 2 divides p. Can we write it over here that p is equals to 2 into something? Can we?
Yes, ma'am.
Similarly, if it is written in the question that 3 divides q, can we write q is equals to 3 into something?
Yes, ma'am.
Similarly, if the statement is, let's say, I'm taking numbers only, 5 divides p square. What can be written over here? P square is equals to 5 into something. Can we write?
Yes, ma'am.
Are you getting it? Everyone, Galvin, Aisha, and Sumaya.
Yes, ma'am.
Are you getting it, Maha?
Yes, ma'am.
Now, these concepts which we are discussing over here, we are going to apply while proving that root 2 is an irrational number. Let's apply it. Okay, carefully we will be doing that. Okay, step by step. Let's do that. We have to show that root 2 is an irrational number.
Ma'am, for root 2, we already did, right?
Yeah.
For root 2, we already did this.
Can you please repeat?
Ma'am, we already did this question.
Root 2 I have done. Okay, let's
Yes.
do with root 3 because last day we have done it quickly. And I said to you that we will be discussing the same concept again because a lot of things we have to keep in mind. Theorem, co-prime number, theorem, this part where we are writing, we are doing the factorization of 24 and then we are saying that 4 can divide 24 completely. Similarly, if we are having the variable m is equals to 2p, then we can say 2 divides m. If k is equals to 3q, we can say 3 divides k completely. If q is square is equals to 2 into k, then we can say 2 divides q square completely. Okay, this is what we learned. Then we also learned that if we will be having just the statement that 2 divides p, we can write p is equals to 2 times something. Okay, if 3 divides q, then we can write q is equals to 3 times something. You need to understand, if 3 divides q means 3 can divide q completely. So obviously we will be writing 3 into quotient part, right? Whatever will be there in the quotient, 3 into quotient part, that is equals to q. Yes or no? If 5 divides p square. 5 can divide p square completely. Remainder is 0. What was the rule? The rule was dividend is equals to divisor into quotient plus remainder. Right? What is dividend? What is divisor? This is how we are having. Let's say we are talking about 8. Okay. 2, 4 times 8. Remainder is 0. This is our dividend. This is our divisor. This is the quotient. And remainder, you already know the bottom one 0 is the remainder. What the rule says, dividend is equals to, the rule says dividend is equals to, dividend that is 8 is equals to divisor into quotient. What is divisor? 2. What is quotient? 4. What is remainder? 0. That's why we are writing. That's why we are writing 8 is equals to 2 into 4. And that's why we are saying that 2 can divide 8 completely, 4 can divide 8 completely. Okay, if we are having just the statement like this, that 5 divides p square, focus on this. If this type of a statement is there, that 5 divides p square, 5 can divide p square completely. Remainder is 0. Okay, so there must be something as a quotient, right? We can write p square is equals to 5 into quotient plus remainder is 0. So that's why we are not writing the remainder. Are you getting it? And that's what you can see. That's what exactly we have written over here. P square is equals to 5 into something. Getting it?
Yes, ma'am.
Are you getting? Are you getting? Aisha,
Yes.
Maha,
Yes, ma'am.
Sneha. Okay, let's
Yes,
prove
ma'am.
that root 3 is an irrational number. Okay, so since we have to prove that root 3 is an irrational number, at first we need to consider, at first we will be taking contradiction method, and there we will be considering that root 3 is rational number. Root 3 is rational number. That's what we are going to consider at first. Okay, we are going to assume that root 3 is rational number. Irrational we have to prove, then reverse we will be assuming, and then at last we will be saying that whatever we have taken as an assumption, that is incorrect. Our assumption is incorrect. Okay, so we are going to take, let's assume root 3 is rational number. Okay, once we have taken this assumption, since it's a rational number, according to our assumption, we can write it in the form of p by q. Yes or no? Or a by b or p by q, where p and q are integer. Can we write it? What was the definition of the rational number? Any number which can be represented in the form of p by q, where p and q are integer and q, the denominator, not equals to 0. Those numbers are rational number. Yes or no? So
Yes,
we
ma'am.
will be saying that root 3 we can represent as p by q or a by b or c by d, whatever you want to take, please take it. Okay. Now here we are going to assume that this p and q are co-prime numbers. P and q are co-prime numbers. We started our class with a discussion of co-prime number, and we have done the discussion that if two numbers are co-prime number, 15 and 8 are co-prime number, then we cannot do the cancellation. There is no common number which can divide 15 as well and 8 as well. Okay, there is no number which can divide 9 and 8 also. These pair are called co-prime number. However, when we have taken 6 and 4, we can see 2 can divide 6 and 2 can also divide 4. So these 6 and 4 are not a pair of co-prime numbers. Okay, so we are going to take the assumption that, let's assume that root 3 is rational number. Since it's a rational number, definitely we can write it in the form of p by q. Okay, now here we are taking the assumption where p and q are co-prime number. Okay, where p and q are a pair of co-prime number. Why we are assuming it co-prime number? We are just saying that there is no common number which can divide P also and can divide Q also. Okay, there is no number which can divide both P and Q. That is the definition of co-prime number. Okay, now so far please let me know, is it clear to all of you? Root 3, we have to prove that it's an irrational number. We started our proof. We started our proof with, let's assume that root 3 is rational number. Okay, contradiction, we have taken the assumption. Now here we are going to, at last we will be showing that whatever assumption we have taken, that is incorrect. Okay, let me wipe this part. We have represented root 3 as a P by Q, where P and Q are integer, of course, and P and Q are also co-prime numbers. Okay, that also we have taken as an assumption only, that it's a pair of co-prime number. Now, we are going to show that there is a common number which can divide P also and Q also, which is against our assumption, co-prime, which will be against our assumption that it's a co-prime. Okay, now only we will be showing that there is a common number which can divide P also and can divide Q also. And then we will say that our assumption is totally incorrect and hence root 3 is irrational number. Let's see how we are going to do that. So now we can write, we can just do the crisscross multiplication over here. See the cursor, we can do crisscross multiplication. We will be having root 3 into Q is equals to P, right? Now, if we will be doing squaring on both sides, what are we going to get? Please let me know. If we will square both sides, squaring both sides. Yeah, please tell me.
3Q square equals P square.
Exactly. Squaring both sides will give only 3. Q square is equals to P square. Okay. That means we can write it as P square is equals to 3Q square. Are we doing any changes? No. We have not done any changes. We have just changed the side. We have written the above step like this. Now, can we say that 3 divides P square? Can we?
Yes.
Yes. Galvin, Aisha,
Yes,
Sumaya.
Yes, ma'am.
Yes, ma'am.
From here, can we make the conclusion that 3 divides P square? Galvin, can we say?
Yeah, ma'am, we can.
This is what we have learned just now. We have written our number 6 as a 2 into 3 and we said that 2 divides 6. Similarly, we have taken example of like a lot of variables we have also taken and we have seen the cases. So like that only we can make the conclusion here that 3 divides P square. Now what the theorem says? What the theorem says? The theorem which we have discussed. If P is a prime number, if P divides A square, then P divides A also. P is a prime number. Okay. So instead of P, we can also have 3, any prime number, 3, 2, 5, any prime number. So 3 be a prime number. If 3 divides P square, then can we say that 3 will also divide? This P is 3. Okay, 3 will divide P. Can we? Can we?
Yes, ma'am.
Are you getting it? Or it is just getting more confusing? Let me know. Yes, Galvin, Aisha, Sumaya, Maha.
It's clear, ma'am.
Yeah, okay. So we are
Yeah,
saying if
clear.
P is 3, P is what? P is a prime number. So 3, P value we can take as a 3. So the same theorem, can we say P is a prime number. That means 3 is a prime number. If P divides A square, that means 3 divides A square. A square, at the place of A square, it can be any number. It can be any integer. Just a second. No? Yeah. So if P divides A square, then P will also divide A. Here we have made the conclusion that 3 divides P square. So can we say that 3 will also divide P? Yes or no? Yes or no? Therefore, 3 will also divide P. From where we are writing that? From the above theorem we are writing that. Yes or no? And we have learned one concept also. Okay, first you let me know, so far is it clear? Let's summarize what we have done. We have to prove that root 3 is irrational number. We are saying that it's not irrational, it's a rational number. If it's a rational number, then definitely we can write it in the form of P by Q. This is just our assumption that root 3 is a rational number. Okay, we can write this rational number in the form of P by Q. See the cursor. Okay, we have written it as a P by Q. Now we are also assuming here that P and Q are co-prime numbers. Okay, there is no common number which can divide P as well as Q. Okay, we have taken P and Q in such a way that this is co-prime numbers. Okay, now we have just done the crisscross multiplication here. We have done is squaring both sides. After doing is squaring both sides, we realize that P square is equals to 3Q square. So we can write it that 3 divides P square completely. Once we have written 3 divides P square completely, now from the theorem we can say 3 will also divide P. Yes or no? So far, let me know. Is it clear to everyone? Galvin?
Yes, ma'am. It's clear.
Aisha? Aisha? Any confusion? Sumaya?
No, ma'am, it's clear.
Okay. Sumaya, to you it's clear. Maha, you said that already that it's clear to you. Let's continue. Yes, Aisha, let me know whether it's whether it is clear or not. Can we continue?
It is clear.
Clear? Okay. Now we have written this statement. We have written this statement that 3 divides P. From the statement, we have learned that if 3 divides P completely, then we can write that P is equals to, dividend is equals to divisor into quotient plus remainder. That means remainder is 0 because 3 divides P. P means 3 divides P completely. And when it's divide P completely, remainder is 0. So we can write from here. We can write from here that P is equals to 3 into quotient. Quotient we can represent by C. Can we? Can we?
Yes, ma'am.
Is it clear to everyone? Just focus on the last 2 lines. Okay, last 2 lines. This last 2 steps. Where I have written therefore 3 will also divide P from the theorem, and then we can write P is equals to 3C. Clear? Now this P is equals to 3C, we can say it's equation number 2, and previously whatever we were having, this we will be writing equation number 1. Okay, now equation number 2, we are going to use we are going to do the substitution that P is equals to 3C. From 2, this P is equals to 3C. We are going to substitute in equation number 1. Okay. P is equals to 3C. We are going to put this value in equation number 1. Okay. P is equals to 3C. Substituting in equation number 1. What was our equation number 1? P square is equals to 3Q square. Our equation number 1 was P square is equals to 3Q square. It was P square is equals to 3Q square. Here we are going to put this P, that is 3C whole square is equals to 3Q square. Let's do squaring. The exponent rule says that what we need to do, we can distribute the exponent to 3 also and to C also. I have mentioned it already in our class that when we are having multiplication, then only we can distribute the power, then only we can distribute the exponent. When we are having division, then only we can distribute this exponent. But when we are having addition or when we are having subtraction, be careful. I have seen most of the students just they do write 3 square plus C square, which is completely incorrect. Okay, they do write 3 square minus C square, which is not true. Here for these two cases we have to apply the identity. But when we are having multiplication and division, we can directly distribute the powers. Okay. So here also we will be distributing the power. 3C whole square will be, can you tell me what we'll be having? Please tell me, anyone. This will become, if we will open the bracket, this will become
9C square.
exactly. Are you getting it? Galvin, who responded? Maha, you said?
Yes, ma'am.
Yes. How, Galvin, are you getting it? How we will distribute the power? Aisha, Sumaya. We will be having 9C square. This square is for 3 also and for C also. It will become 9C square. Other side is just 3Q square. Then we will be doing the cancellation. Here 9 is there, here 3 is there. If we will take this 3 to other side, this 3, if we will just transpose it to this side, it will become Q square over here. And there it will be 9 by 3 C square. That means 3 times 9. 3C square is equals to Q square we got, which we can also write it as Q square is equals to 3C square. Now what can be written over here? Please let me know. What can be written? 3 divides
3 divides Q square.
exactly.
Hence, 3 also divides Q.
Exactly, 3 divides Q square, and therefore 3 divides Q. Okay, this one we are just concluding from the theorem. Okay, now 3 divides Q we have written. Here we have written here we have written 3 divides P, 3 divides P, 3 divides Q. But initially we have taken the consideration P and Q are co-prime number. Co-prime number means what? There is no number which can divide P also and Q also. Okay, apart from 1, there is no common number which can divide P as well as Q. But here we ended up getting 3 divides P, see the underlined part, and we also got 3 divides Q. Hence our assumption, here we will write, but P and Q are co-prime numbers. Hence, our assumption that root 3 is an irrational number. Rational, we have taken the assumption, no? And then we will conclude that our assumption is incorrect. Rational number is incorrect. Our assumption, which we have taken initially, that root 3 is rational number. We can write it in the form of P by Q, where P and Q are co-prime. It is false. Okay, it's not correct. Our assumption is incorrect. Therefore, we are done with the proof that root 3 is an irrational number. This is how we will prove it. This is how we will prove for root 2, root 3, root 5, any irrational number. This is how we will be proving it. Okay. Hence, we have summarized what we did over here. Just a second. Let me know if you are having any doubt in this concept. Today, you won't be able to give the assessment which is related to this concept, because few more irrational numbers are there, which we will be proving, that it's an irrational number. Apart from root 2, root 3, root 5, I believe now you must be able to prove this type of number, square root number. If single square root number is there, then definitely we will be able to prove that it's an irrational number. How? Just by applying the same approach. We have to first assume contradictory method. We have to take the contradiction. Contradiction means the reverse, opposite, exactly reverse thing we have to assume. Okay, so we are assuming that root 3 is irrational. We have to prove, we are assuming that it's a rational number. Since it's a rational number, we can write it in the form of P by Q. Then what we are doing, we are just doing is squaring, and whatever we have got, that we are mentioning equation number 1. From there, we can make one conclusion that 3 divides P square. If 3 divides P square, then definitely 3 will divide P also from the theorem. Okay, if 3 divides P, then we know how to write it in this by using the dividend is equals to divisor into quotient plus remainder. This is how we can write it. Quotient we don't know. So for quotient, to represent the quotient, I have used this alphabet C. You can take Z, you can take any other number, okay, to represent your quotient. Here we just want to write 3 into quotient Q. Okay, for quotient Q, you can take any variable. This is how we are representing it. Now, equation 1 and equation 2, we are doing the substitution from equation 2 to equation 1. And after doing the substitution, this is what we are getting. Okay, this is what we are getting. Q square is equals to 3C square. Again, we have to repeat the same process, that 3 divides Q square, 3 divides Q, which is